Hi everyone, welcome back. This video will address the following question. Why does the acceleration of a skier increase as the steepness of the slope increases? A seemingly obvious question, but underlying that is some really important principles. So this video will look at the essential skill of resolving forces into their components, which includes analysing components of weight. This is a fundamental principle and skill which is needed not only for the mechanics topic, but throughout the entire A-level course. I hope you enjoy the video. Okay, so components of forces is quite a tricky idea. A lot of students struggle with this. So before we go straight into, or rather than going straight into the mathematical analysis, it's quite nice to have a little thought experiment. So if you imagine a horizontal rope with some weight, for example a bird resting in the middle, and then you've got a student at either end, or maybe a team of people in a tug of war, and the challenge is to pull the rope or make the rope horizontal. Is that possible? That's the thought experiment. Now you may even see by this little dip here that it's not possible, and we need to know, well, why is that? And this is all to do with forces and equilibrium. So we've mentioned already earlier on in a previous video that in order for things to be in equilibrium, balanced, then the sum of the forces in all directions must be equal to zero, or in any direction. In other words, the vertical forces must be balanced. So we have a weight of the object, the bird, and the weight of the rope itself acting downwards. So in order for this to be stationary, something must be pushing upwards. So something needs to provide a force acting upwards. And the only thing in this system that can do that is the rope. So part of the rope, part of the tension in the rope must be acting upwards. And this is known as the components, or in this case, the vertical components of tension, in order to balance the downward weight. So this leads us into this idea of components of forces, but in fact any vectors. So very often we do talk about components of forces, but this could be applied to components of acceleration or displacement or any other vector. So if I have a force F at an angle, let's say an angle to the horizontal theta, then I can draw a right angle triangle as shown here, and then I can consider these two sides, and those are the components, the horizontal component and the vertical component. And we've done this already, trigonometry. If this is a right angle triangle, then my adjacent side, according to SOHCAHTOA, this will be F cos theta, and my vertical side will be F sine theta. So what we're doing here, this is called resolving a force, splitting it into its two components. And it's basically the opposite of what we've done previously. So in the previous video we talked about getting, thinking about resultant forces, maybe this horizontal and vertical force combining together to make a resultant force here. And this is basically the opposite of that. But it's very, very similar. It's still a right angle triangle, and it's still a SOHCAHTOA trigonometry. So this is a really, really useful idea, and not just for mechanics, but all the way through physics A level, we will refer back to components of force or components of vectors. And a really important point here is that these two are independent of each other. Because they're at 90 degrees, they're independent. Now that won't mean much in what we're doing today, but later on, in fact, when we look at projectiles, later on in this series, then that's a really, really important idea. Okay, so a simple worked example. If I have 50 newtons acting at 30 degrees to the horizontal, I can draw a right angle triangle and consider the two components, the horizontal component X and the vertical component Y. And I know if it's the adjacent, it's going to be cos. So 50 cos 30 will give me the horizontal component, 43.3, and 50 sine 30 will give me the vertical component, 25. And that's it. It's a nice, simple trig calculation, and it's very, very useful, as we will see. So let's look at a slightly more complex worked example. And this is a really typical example for exam questions. The examiners love writing this type of thing. So you have an object in equilibrium. The object has a weight, and there may be, as in this case, two ropes with a tension, you might be given one tension and not the other tension. And sometimes there are different ways to solve this. Now, if we could draw a right angled triangle, that would be fine. We could just draw a triangle of equilibrium and use Pythagoras and trigonometry to solve this. But we can see that this will not give us a right angled triangle. So we could draw excuse me, a scaling triangle and use the sine or the cosine rule, even though that tends not to be on the A-level spec. We could draw a scale drawing, but that's not very precise and it's a bit fiddly. So the best way to solve this would be to consider the components. Now in this question, it's led us into it quite nicely. It says find the vertical component of the 7.6. Okay, well that's nice and straightforward. So I can imagine I've got a right angled triangle here. I'm trying to find this red upwards component here. So yeah, it's the opposite, so it's going to be sine. 7.6 sine 40 will give you 4.89. So a nice easy bit of trig there. So we've got to think, okay, well we're in equilibrium, as it says here. So we've got the 15 newtons acting downwards. We've got the 4.89, the vertical component of the 7.6 acting upwards. So something else over here must be also adding to this 4.89 to balance the 15. So it says find the vertical component of t. Now very often students will think, right, I need to consider what t is, but we don't know what t is. We haven't been told that, and that's actually part C. So the way we do this is, as we've alluded to a minute ago, is we need to consider the forces acting up. So the sum of the forces acting up must be equal to the total force acting down. In other words, 15 acting down must be equal to this unknown value here, shown by the green arrow, plus 4.89. So this actually becomes a very straightforward mathematical calculation. So the total force down is 15, total force up, 4.89 plus the vertical component t. So all we need to do is to subtract 4.89 from the 15 and we get 10.11. Okay, so what we said here is 10.11 plus 4.89 is 15 newtons in total acting upwards, which is balanced by the 15 newtons acting downwards. Brilliant. Right, so we're nearly there. Now we're trying to do part C. It says find the value of t. Okay, well if I complete my triangle here, well, I've got a right angle triangle. I can use trigonometry to find t. But we have to be a bit careful. Obviously we've got the adjacent, so we're going to use cosine. But a very common mistake here will be to calculate 10.11 cos 30, which would give us a number smaller than 10.11, which must be incorrect. So we have to be careful with our SOHCAHTOA here. So we know that cos of the angle is the adjacent divided by t. So to make t the subject, that'll be the adjacent divided by cos 30. So if we divide by a number smaller than 1, we get a larger value, which should make sense. So the t is the hypotenuse. That must be larger than 10.11. Otherwise we made a mistake. Okay, so a fairly straightforward example, but really important. This type of question comes up a lot in the exam. And also, as mentioned previously, this type of question will crop up in other topics later on in the course. It's not just restricted to mechanics. Right, the second part of the video, we're going to consider components of weight. Again, this is really, really important, and a lot of students get very, very confused by this. So definitely worth spending a bit of time on. So again, we're going to introduce this with a concept question. So if you imagine you're a skier, and the steeper the slope you ski down, then the faster you go, the bigger your acceleration. The question is, why is that? And that sounds like a bit of a daft question because we know that intuitively. If we increase theta from the horizontal, then the acceleration will be greater. You're going to move down this slope more quickly and reach a greater maximum velocity. Why is that? How do we explain that? So this is what we need to address here. So the first thing we're going to consider is what are all the forces acting on the skier. So we have the weight. We always have the weight acting vertically downwards. We have a reaction force. Now we've got to be careful here because up to this point we've always considered reaction force where the surface is horizontal. Therefore the reaction force will be at 90 degrees and be vertical. But by definition the reaction force is also called the normal force. It must be at 90 degrees to the surface. So it's going to be as shown here. Friction always opposes motion. That's going to be acting up the slope. So What we're going to do here is consider the components of the weight acting parallel and perpendicular to the surface. Okay, so we're going to draw a right angled triangle as shown here. We've got the weight as the hypotenuse. We're going to draw a line here which is perpendicular to the slope, that's at 90 degrees. And the other line, the other component is parallel, that's in the same direction up and down as the slope. And this is our right angle over here. So the weight must be the hypotenuse of the triangle. And theta is always going to be the same as the angle of elevation. Now, we can show why that is the case. If we pop this over here, then if you imagine we've got 90 degrees here, this one's going to be theta minus 90. So if this angle here in total is 90 degrees, then this must be theta as well. So we can show why that is through geometry, but it's always going to be the case. So we always know theta because that's the same as the angle of elevation. And then we can just apply SOHCAHTOA. So if I'm interested in the perpendicular component here, that's the adjacent, so that's going to be the weight times cos theta. And the parallel component, that's the opposite to the angle, so that's going to be W sine theta. So this is straightforward SOHCAHTOA, but it causes a lot of confusion because it's different to what we've seen before. Now, what's really useful is just to consider, is just to rotate this, and obviously all the words are the wrong way up. But if you imagine what we've just done previously, we had a force, we had an angle, and we worked out the X and the Y components using SOHCAHTOA. And that's exactly what we're doing here. We're just considering the components of weight, not in X and Y, but perpendicular and parallel. And it's worth considering why we don't use the X and Y components. Well, it wouldn't make any sense because if you ask what is the horizontal component of weight, which is a vertical force, the horizontal component must be 0. And the vertical component of a vertical force is just the force itself. So using the X and Y components here doesn't make any sense at all. However, the perpendicular component, well, that's useful because nearly always that's going to just be equal to the reaction force, which is quite handy. And then also, the parallel component is really useful because that is our motion. We are moving down the slope or possibly moving up the slope, so the parallel component is really, really useful. So going back to our initial question, why does the acceleration increase as the gradient increases? As the slope gets steeper, the component of weight parallel to the slope increases. Therefore, we have a greater accelerating force down the slope, and the acceleration is greater according to F equals ma, Newton's second law. Okay, so lots and lots of information in there, but effectively all we're doing is right angle triangle, SOHCAHTOA. Right, before we look at a couple of worked examples, just worth mentioning, a lot of students make this mistake. It's very, very common. And obviously this will mess up your answer and your understanding as well. Very often students draw their triangle like this. So we got the weight, that's fine. And then rather than draw a parallel component, parallel to the slope, they draw this horizontal line here. Now that must be incorrect because it must be a parallel component, not a horizontal component. The horizontal component of weight is 0, so it doesn't make any sense at all. Also, and very importantly, if we draw it like this, then this component here, the perpendicular component, becomes the hypotenuse of the triangle. Again, doesn't make any sense because that would mean a component of the weight is larger than the weight itself. So we have to redraw this correctly. We've got the parallel component and the perpendicular component. The right angle is here, and we have our hypotenuse, which is the weight. Right, let's have a look at a simple worked example. So we've got an object on a slope, it's got a weight of 30 newtons, we have angle of elevation of 35 degrees. So very often the exam question will say, part 1, draw the vector triangle. Now even if it doesn't say that, you should always draw it to avoid making a mistake. So we've got our 30 newtons is the hypotenuse, 35 and 35, that's always the case. And then we can just do part 2 and part 3. Calculate the parallel component. This is this one over here. That's going to be opposite, so it's W sine theta, 30 sine 35. The perpendicular component, that's going to be adjacent, W cos theta, 30 cos 35. And we've got part 2 and part 3. It says state the reaction force. Well, the vast majority of the time, unless we have a very complex situation, the reaction force, which is the normal force, will be equal to the perpendicular component. So it's just the same as part 3, 24.6. And there's a bit of a clue here. Very often, if a question says state rather than calculate, and usually it'll just be for 1 mark, that usually means, not always, but usually, you don't have to do a calculation. You're just writing down one of your previous answers. So that's a nice exam tip for you there. Right, a final example, slightly more complex, and again, really typical question from the exam. So you have an object, well, we've got a man with a mass, we have an angle of elevation. In this case, we're told the frictional force, and we're trying to calculate the acceleration down the slope. So the first thing we should do is to draw our component triangle. So we've got our perpendicular and parallel component here. We could also add on the friction as well, because that is non-zero in this case. In fact, another thing we have to do, and this is a very common mistake, because it's told us the mass, well, all of this is working in forces. You cannot calculate the component of the mass because mass is a scalar quantity, so that wouldn't make any sense. So actually the first thing we need to do is to calculate the weight in newtons. mg, we get 638. Yeah, we probably wouldn't be given the hint in the exam. It might break it down into ABC, but probably not for a question as straightforward as this. So we're interested in the motion down the slope. So the first thing we have to do, as per the hint, is to calculate the component of weight down the slope. So we have W sine theta. Theta is 45. We've got the weight 638, and we get the component is 451. So that's the red arrow here. Now we could calculate the perpendicular component if we wanted to. We don't need to in this case, but in another question that might be useful. Right, so the resultant force acting down the slope. So we've got 451. If this was starting from zero velocity, or if it was a friction-free or limited friction slope, then it would just be 451 acting down the slope. But we have 185 acting up the slope over here, so we need to subtract that from 451 to get 266. That is our resultant force. And then we're trying to find the acceleration. F equals ma, Newton's second law, A equals F over m. So our previous answer, 266, divided by, be careful, the mass of 65, not the weight. So just the m, not the w, and we get 4.1 or 4.09 meters per second squared. So that's more like what you'd get in the exam, but again, they probably will be more difficult than this, and there might be other things to consider as well. Right, well done. There's a lot of really important ideas we've just considered there. So that is components of vectors, components of forces, and then in particular, components of weight. So the next thing you could look at, you could go straight onto the work, power and energy, but there actually is a video on projectiles, which again, really important, quite difficult ideas. I recommend you check that one out. Alternatively, or you could go to payhit.com, grade A physics, and there are structured lessons, lots of quizzes, lots of exam tips, and lots of work solutions. Hope you enjoyed that. Any ideas or comments or feedback, please add some comments in the box below. See you next time. Bye.